So I'd like to introduce Willem Marais. He received his undergraduate in computer engineering at University of Pretoria in South Africa. After that, he worked on the Council of Scientific and Industrial Research as a remote sensing specialist before he decided he wanted to go back to school, and received his master's degree at University of Wisconsin-Madison and has continued on to work on a PhD in electrical engineering with a focus on signal processing. His research focus is on bringing advanced algorithms for signal processing to remote sensing problems, and that is mostly focused on denoising low SNR data and improving inversion algorithms. And Willem is slated to graduate this year by the end of the calendar year. So with that, I'll let you take over.
Thank you, Matt. So can I, just by raising up your hand, can you tell me if you're a LiDAR expert? Are there any LiDAR experts? Oh, there's a couple. And then any radar experts? Okay, so I just want to get a general feel of the audience. Okay, so as Matt said, obviously, I'm Willem Marais. It's like the person there on the left. So I work with Robert Halls, and as some of you know, Ed Aloranta. And then, so I'm an engineering student working with atmospheric scientists. So my advisors are Ewan Hu and Rebecca Willett, and Rolf Keen is a colleague of us that helps me manage the LiDAR data and work with the LiDAR data. So today I'm going to, well, like Matt said, I'm an engineering student who specializes in signal processing algorithms. And my research goal is to take signal processing algorithms that have been developed in medical imaging and statistics and other kinds of domains and incorporate it into atmospheric science. A lot of advances have been made, and let's say medical imaging, algorithm development, and we believe that the LiDAR community, and maybe also other remote sensing communities, can benefit from the advances that were made. So let me state my long-term research goal. And let me do it by introducing a problem. So what image you see on the slide is a LiDAR image that was acquired by the Calliope instrument, a LiDAR instrument that's on board the Calypso satellite. Calypso was launched more than 10 years ago. So, and since Calypso was launched 10 years ago, we have more than a 10-year data record of LiDAR measurements that were made across the whole globe. And the specific measurements that are made is what we call the attenuated backscatter coefficients. And with it, you can infer the extinction coefficient, or the extinction cross-section, as we call it, which is used in radiative transfer models for climate modeling and improving climate models. So it's an extremely valuable data set. Like, it's the first of its kind. It's more than like the size of it is humongous. As you can see, okay, so also with LiDAR, you have high vertical resolution measurements that you make of the atmosphere. So you can get high vertical resolution measurements of the extinction coefficient of clouds and aerosols. The problem is, as you can see in this image, it looks very grainy, and that's the noise. Since the satellite is, or the Calypso satellite is roughly more than 500 miles away from the Earth's surface, and it can only transmit, well, it has limited energy with which it can transmit to laser pulse, it basically receives a very low signal-to-noise ratio signal. So the detectors it uses introduce a lot of noise when it makes its measurements. So that's one of the sources of the noise that you see. Also, in addition to that, we have the sun, and the Calliope instrument transmits a visible wavelength laser pulse. So it makes measurements in the visible wavelength space. So you have the solar background radiation that adds to the noise, because there's solar background radiation that's reflected by the Earth's surface and clouds. So you have those two noise sources that really adds noise to the image, and it makes it harder to work with your LiDAR imagery. So obviously, one way of reducing the noise is if you want to retrieve the extinction cross-section or coefficient of water clouds and cirrus clouds and desert dust, is by binning the image or averaging the profiles of the image to reduce the noise variance. Great, you can reduce the noise variance by averaging data, but the problem is you introduce systematic biases in your extinction coefficient, because there's a nonlinear relationship between the measurements you make, the attenuated backscatter coefficient and the extinction coefficient. And it's not easy to correct for those systematic biases, since there's a non-linear relationship between the extinction coefficient and the measurements you make. So my research goal is to find different ways of advanced signal processing ways of removing the noise while keeping the LiDAR image at a maximum possible resolution. And by doing so, we introduce less systematic biases in the extinction coefficient that's been retrieved. Yes, so even though I show you a space-based LiDAR image, we started our research with using a ground-based LiDAR system and using a specific type of LiDAR instrument called a high spectral resolution LiDAR imager that allows you to retrieve the extinction coefficient in a much more constrained way. You can uniquely estimate the extinction coefficient. And so we started our research off with that type of instrument, and then uses fountain counting mode detectors to make its measurements. And our long-term goal, which I have not achieved yet, but will eventually arrive to it, is removing the noise of satellite-based imagery. So the results I can show you in this presentation is results that we were able to achieve with a ground-based LiDAR system, but not yet with a satellite-based system. So since most of you are not LiDAR experts, let me just give you a brief introduction. Yes?
Quick question. How do you define SNR threshold, low and high? What is your limit on SNR?
The way that LiDAR experts determine, I think, whether the SNR is high enough is to look at their uncertainties of the retrievals they make. If the uncertainties are low enough, then the SNR is high enough. So you look at the uncertainties of your retrievals to determine if your SNR is high enough. Does that answer your question? Okay. I can't think of I don't know of a threshold.
Like with the radar, we say, okay, 10 dB is lower than, what kind of some dB level, kind of noise lower like that. Is that number code like that?
So we work with an inversion problem, and so it's hard to say what the threshold is. I can't give you a threshold. Okay, get back to this slide. So let me give you a brief introduction of LiDAR. So the LiDAR instrument that we are focusing on transmits a laser pulse at a visible wavelength. The one that specifically we work at, it transmits at a 532 nanometers, which is green light. As the laser pulse traverses through the atmosphere, we have ice crystals, dust particles, water droplets, and everything else and molecules that scatter the photons. And as the laser pulse propagates, it gets attenuated due to the scattering by the ice particles and water droplets and molecules. But also because we are at a fixed location with the LiDAR instrument, the laser intensity decreases as the altitude increases of the laser pulse. So our signal strength decreases at a rate of 1 over altitude squared. So we work with low SNR data if you make high altitude measurements. And then what the LiDAR instrument measure is what we call the 180 degree backscatter. So the previous slide that I showed you was what we call a standard backscatter LiDAR image, where you only have a single channel. We measure both the particulate and molecular backscatter. So you can't really make a distinction between the molecular backscatter and the particulate backscatter. But with the high spectral resolution LiDAR imager, which I will introduce in the next slide, you're able to make a distinction between the molecular backscatter and the particulate backscatter. The way you do it is that since the size of molecules are comparable to the wavelength at which you transmit the laser pulse, and because molecules are in a random motion, like a Brownian motion, if I pronounce it correctly, the molecular backscatter experience what we call a Doppler broadening. So the energy of the laser pulse gets spread over to different wavelengths, as you can see in the slide. So you see a Gaussian pulse, and this Gaussian pulse is the Doppler broadening induced by the molecules, and what you measure, and that's the molecular backscatter. Particulates are larger than molecules, and I don't introduce much broadening compared to molecules. So the particulate signal that a LiDAR instrument measure it doesn't have much broadening over the different wavelengths. So all its energy is focused on a specific wavelength at which the laser pulse was transmitted. So what you can do is you can use an optical notch filter to remove the backscattered energy of particulates. Then you end up with only the molecular backscattered energy. And then if we make two sets of measurements, you can separate the molecular backscattered energy and the particulate energy. And what that allows you to do is then you can, for one, you can get the optical depth of particulates, you can get the backscatter cross-section of particulates, and as we'll show in this couple of slides. So the top left-hand image shows you where the photon counts that were measured by the ground-based LiDAR instrument, and the photon counts you see is due to both particulates and molecules. So high up in the atmosphere, you see cirrus clouds that scattered the photons. You have an aerosol layer in the middle, probably dust or smoke, and then you have the boundary layer at the bottom. And you see at the backdrop, the signal strength decreases, and it's due to the laser intensity that decreases as a function of altitude, and the molecular backscatter due to the air pressure that changes, or this decreasing. The most right top-hand image is the molecular backscatter, and so as you can see, as a function of altitude, the molecular backscatter energy decreases monotonically because the molecular density changes as a function of altitude. One thing that I want to point out to you is that just to backtrack, so high spectral resolution LiDAR imager make two sets of measurements and it has two channels. So you have the combined channel and the molecular channel. And the molecular channel SNR is smaller compared to the photon of the combined channel, and that will introduce several problems. For instance, the retrieved optical depth using the high spectral resolution LiDAR imager is noisy, and that will become a problem later on when we retrieve the extinction cross-section. What we also get is the backscatter cross-section, and that's of the particulates, and that shows you clearly where the clouds are, the aerosol layer, and the boundary layer. So to get the extinction cross-section, you take the optical depth, and you take the derivative over the altitude axis. And this is what you get. So this image, the top left-hand image, shows the extinction cross-section after you take the derivative over the altitude axis of the optical depth. And just to tell you where the clouds are and where the aerosol layers are, the bottom image shows the backscatter cross-section of the particulates. Now, there's not much you can see because there's so much residual noise in the extinction cross-section. It looks kind of pointless to use it and useless. So one way the reason why it's pointless and useless is that there's so much residual noise in the optical depth. So if you want to have any meaningful results, by taking the derivative of the optical depth to get the extinction cross-section, you have to remove the noise in the optical depth. One way of doing it is, and it's the way Ed Elorante does it, and I'm sure that other people are doing it, is that you take the optical depth, you apply a smoothing filter over it, a low-pass filter, you remove the high-frequency component noise, and then you take the derivative of the filtered optical depth, and then you get the extinction cross-section. So this image, the top right-hand corner image, shows the extinction cross-section after you apply the low-pass filter on the optical depth. So you can at least make out the features like clouds, the middle aerosol layer, and then the boundary layer. But there's a couple of problems. One, the extinction cross-section is totally smoothed out. It's like you don't see the variability of the extinction cross-section inside the cloud. It's just a smooth surface. We see non-uniformity or variation of the backscatter cross-section inside the cloud, but you don't see it in a retrieved extinction cross-section after low-pass filtering the optical depth. And the boundaries of the clouds are smoothed out. That's a problem because then your extinction cross-section is biased, and there's a lot of artifacts in that image. That's not ideal. That's not what you want to work with. You want something that's less biased, has less artifacts, is more workable, more useful. So the reason why low-pass filtering doesn't work is that there's a couple of assumptions that you make when you do low-pass filtering. First of all, you assume that the signal that you're trying to estimate is a slow-varying signal, which is not clearly the case because the extinction cross-section has boundaries around the clouds. So there's a high-frequency component that the low-pass filter doesn't take into account, and you have non-uniform structures in an extinction cross-section, which the low-pass filter doesn't take into account. So to use the low-pass filter to remove the noise so that you can get the extinction cross-section, it's you basically make a false assumptions. So we have to find a better way of modeling the image of the extinction cross-section to get an improved estimate of the extinction cross-section. So what you see in this slide is, here's the low-pass filtered optical depth from which we get the extinction cross-section after taking the derivative. And this image shows a result of an algorithm that we developed to retrieve the extinction cross-section. What you immediately see of the image of the retrieval that we made with our new approach is that the cloud boundaries are not smoothed out. You see variability inside the extinction cross-section, inside the clouds. You don't see significant artifacts compared to this image we're using the low-pass filter approach. So it looks arguably better. When I showed this result to Ed Laurento, the compliment he gave me was, it looks like snake oil. It doesn't look true. How can this be true? Is this really, it looks good, but is it really a good result? It's like, it seems too good to be true. So I can try to convince you that what we are doing is reasonable and does give reasonable results. It's based on well-founded principles from optimization, statistics, and signal processing. But let me tell you why our new approach is actually giving good results, why it's doing a better job compared to the low-pass filter approach. Current LiDAR algorithms, most LiDAR algorithms basically estimate the parameters they want using single-point estimates. In other words, if you have an image and you have a specific pixel and you want to estimate of that specific pixel of the parameter, you don't use that specific pixel normally, usually. But if we look at this image, there's a lot of structure in the atmosphere. In other words, if we have a noisy image and we want to remove the noise and estimate the parameters that we want, rather than estimating our parameters at every single point in the image, we can use the spatial structure of the atmosphere as a priori information and use that to basically remove the noise and get better estimates of our parameters. So in other words, we use the spatial correlations, two-dimensional spatial correlations of our extinction cross-section or backscatter cross-section to get a better estimate of the extinction cross-section. So let me explain to you what I mean by spatial correlation or exploiting the spatial correlation. Just to backtrack a little bit, like I said, most LiDAR algorithms estimate either using a column of an image or they use points of an image rather than looking at the whole image. We take a different approach and we say, let's use the whole image, all the available information to get a better estimate of the extinction cross-section or the backscatter cross-section. I can use a one-dimensional signal to explain to you how we exploit the spatial correlation of an image or of a signal. But that can be generalized to a two-dimensional image. Also, while explaining how our estimator works, and I can explain to you how we denoise the photon counts. We denoise the combined channel photon counts and the molecular channel photon counts. By doing so, we then have, we get the estimates of the backscattered energy measurements of the combined channel and the molecular channel, and through that we can get the backscatter cross-section, which we'll use later on to get the extinction cross-section, which I'll explain in a couple of slides from now. So what you see in this slide, and the blue graphs show the combined channel photon counts and the molecular channel photon counts. And obviously it looks very noisy. It's not what you want to use if you want to get the backscatter cross-section or the extinction cross-section. So like I said, the molecular channel, or the molecular backscattered energy, is a monotonically decreasing function. And it's arguably a smooth varying function. I think that's safe to assume. So we can approximate the molecular backscattered energy with one way of doing it is by a piecewise constant function. The same with the combined channel measurements. Like we have a cloud that's situated above 14 kilometers, but below the cloud is just, there's no clouds and no aerosols, obvious aerosols. It's a slowly varying signal. So we can estimate parts of the image by a piecewise constant function. So why I say piecewise constant is that, like I said, with a low-pass filter, you assume that your signal only has slow varying components. But if you were to take an image and approximate it with a piecewise constant function, you can accommodate any high frequency changes. In other words, where there's jump discontinuities, like we see above here, we have a jump discontinuity in the signal. So what you do is, intuitively, if we were to look at the signal, and what we mean by correlation, if pixels are correlated with one another, and you look at one pixel, and if you look at the consecutive pixels around it, they should be very similar in magnitude. So what you can do is, if you want to fit it on the noisy data, like we have here in the blue graph, you can approximate those correlated points with a constant line. So whenever you have pixels or lines or points that are very correlated with one another, you just approximate it with a constant function. But in doing so, because there's changes in the function you're trying to estimate, you have to adjust the length of your piecewise constant estimate, and you have to, if you use different piecewise constant estimates, you have to take into account their differences in between each other. For example, what you see in this graph is like when you estimate the backscatter cross-section, the algorithm, what it did, is like it takes points that are correlated with one another and estimate a constant line. And then it looks at and then see wherever there's more points that correlate with one another, and it estimates a constant line. Said in another way, what it's trying to do is it's trying to take an estimate, or create an estimate that is trying to fit on the noisy observations. And it's trying to find an estimate that has the smallest amount of variation. It only allows variation where there's changes in the signal. So if you look at this noisy signal, the blue graphs, it's like the noisy signal has a lot of variation. But the signal that we're trying to estimate has a lower amount of variation. So you're trying to estimate a signal onto the noisy observations that has a smaller amount of variation. And that's basically the principle upon which the denoising algorithms are based upon. It's like you estimate a signal that has a smaller amount of variation. Since your criteria for fitting an estimate on a noisy observation is how much it varies, you allow for discontinuities, as you can see in this image. It's like we denoise the combined channel, it fits a line over the discontinuity, and it chooses the optimal jump discontinuity of the estimate onto the noisy observations. So to explain it in a different way, in a more principled way, is that, like I said, you have your noisy observations, and you're trying to fit your estimates onto the noisy observations. The way you do it is you take, since we know what our noise is, for phonic counting systems, lidar systems, the noise you deal with is what we call Poisson. It's Poisson noise, and it can be modeled with a Poisson probability mass function. You can take that probability mass function of the noise, and you can derive from it what we call a fitting function. The fitting function tells you if you have an estimate of the noisy observations, how close your estimate is compared to the noisy observations. So what you see in this slide, the L is our fitting function, chi is our estimate, and y is the noisy observations. So the function L, if chi is very close to y, meaning chi is very close to the noisy observations, the fitting function is a small value. So the smaller the fitting function value is, the closer our estimate is to the noisy observations. So that gives us a way to quantitatively find an estimate that fits into the noisy observations. The a priori information that we have is that our estimate has to be piecewise constant. It's like this is our smoothness criteria. That's our way of making sure that our estimate is not noisy, but it's smooth. So what you do is you take your fitting function, you vary your estimate, chi, and you minimize your fitting function as a function of your estimate, chi. While you're doing that, you constrain your estimate chi to be piecewise smooth or piecewise constant. And we do that by upper bounding or limiting the total variation of your estimate. All of this can be cast into a mathematical optimization framework. And by doing so, you're finding an estimate of the noisy observations. in a well-principled way, in an optimal way. I should also say everything is done as a whole image. It's like all the pixels of the image, as you're trying to find the estimate of the noisy observations, are all varied simultaneously. It's like the whole image is varied until you find an optimal estimate that fits onto the noisy observations. So using these principles or these methods, we can then denoise the combined channel and the molecular channel. As you can see in the previous two slides, it's like the red graph shows the denoised combined channel and denoised molecular channel. And once we have a denoised combined channel and denoised molecular channel, then we can estimate the backscatter cross-section, which is great because it turns out there's a high correlation between the backscatter cross-section and the extinction cross-section. In other words, if we know what the backscatter cross-section is, then we can use that as a priori information to estimate the extinction cross-section. So what we have is then, well, let me backtrack a little bit. So in the LiDAR community, one parameter that's normally defined is what we call the LiDAR ratio. The LiDAR ratio is the ratio between the backscatter cross-section, the ratio between the extinction cross-section and the backscatter cross-section. So it's basically, the inverse of that tells you if you have a pure scattering medium, what's the percentage of energy that gets scattered back towards the LiDAR receiver. It's also known as the 180-degree backscatter phase function for a pure scattering particle. So, like I said, the LiDAR ratio is the ratio between the extinction cross-section and the backscatter cross-section. We know what the backscatter cross-section is. So rather than estimating the extinction cross-section, we can estimate the LiDAR ratio. I think it's generally safe to assume that you can accurately approximate the LiDAR ratio by two-dimensional piecewise constant function. I think it was what most LiDAR experts do. And then, so we have a smoothness criteria that we have our LiDAR ratio, onto which we can fit onto the photon counting observations. And once we have an estimate of the LiDAR ratio, we could then multiply it with the backscatter cross-section, and then we get our extinction cross-section. And this is what I'm going to show you how we do it. So we have our molecular channel forward model that models what the molecular channel observes, the molecular backscattered energy. We parameterize it with the LiDAR ratio and put into it the backscatter cross-section that's fixed. So the extinction cross-section is basically replaced with the multiplication of the LiDAR ratio and the backscatter cross-section. Now we have a forward model that describes to us how, if we have a LiDAR ratio, how does it fit onto the molecular channel observations. So we can take that forward model and put it into our fitting function that we derive from our photon counting noise. And that's what this L with the composition with the forward model indicates. And we have our molecular channel photon counting observations. So what this tells us is that we can take the LiDAR ratio, vary the LiDAR ratio, and see how the forward model of the molecular channel fits onto the molecular channel observations. And therefore, we can then minimize the fitting function as a function of the LiDAR ratio. And while we're minimizing the fitting function, by varying the LiDAR ratio, we can constrain the LiDAR ratio to be piecewise constant, two-dimensionally piecewise constant. And then we can get our estimate of the LiDAR ratio, multiplied with the backscatter cross-section, and voila, we have our extinction cross-section. And this is how we retrieve our extinction cross-section. And this is why we get such high-quality results, because our model allows for discontinuities in the extinction cross-section and allows for non-uniformities in the clouds and the aerosol layer of the extinction cross-section. So the method that I explained to you, or the methods that I explained to you, has been published last year, 2010, so it has been peer-reviewed. The paper includes results using simulations, and we apply the technique on real data, and we compare it with the low-pass filter approach. We're currently working on a paper now where we're going to derive the uncertainties of our extinction cross-section and LiDAR ratio. So we have to publish it or submit it by this year. So I explained the technique to you. I showed you one result. Let me show you another result that's interesting that we got when we started doing research with Jeff Reed. Jeff Reed asked us to do an inversion of the extinction cross-section of a high elevated aerosol layer. The data was acquired in 2013 in Huntsville during the Seekers campaign. So in this image, you see the backscatter cross-section, or the parallel polarized backscatter cross-section of a very high altitude aerosol layer. The reason why I say it's an aerosol layer, or part of it is an aerosol layer, is that you have low depolarization of some parts of the aerosol layer, or the elevated layer. So you can see to the left of the aerosol layer, there's low depolarization, but at the bottom, over here, you have high depolarization, which indicates that the particles are non-spherical, highly irregular, which possibly means that it's ice particles that's suspended below the aerosol layer. It's very interesting. So we're curious of what lidar ratios you get and what the extinction cross-section looks like. So this slide shows you, the leftmost image shows you what the extinction cross-section would look like if you were to use Ed Oloronta's approach, or using a low-pass filter to remove the noise of the optical depth and take the discrete derivative to get the extinction cross-section. Unfortunately, you don't get much, well, you get some information about it, but you have a lot of artifacts, and the variation of the extinction cross-section is smoothed out inside the cloud. This is not ideal, but whereas the new approach, we're able to maintain the non-uniform structure inside the cloud to a high degree. We don't ever smooth the boundaries of the cloud, and there's way less artifacts compared to the old approach. So you can see the extinction cross-section, even though the backscatter cross-section is very low, the extinction cross-section is very high, relatively speaking, and indicating that the lidar ratios are large, and that's what we see in this next slide. Again, the leftmost image shows an inversion result using Ed's method, or retrieving the lidar ratio. To retrieve the lidar ratio, you need a very high SNR signal. In other words, you have to do a lot of averaging. Since we try to do retrievals or inversion on low SNR data, meaning the spatial resolution is at the highest, Ed's Oloronta's method doesn't do a good job. You do see some structure. You see low lidar ratios at the bottom of the aerosol layer, but otherwise the lidar ratios are off the map for the rest of the aerosol layer. Whereas the method that we developed, you see lidar ratios of the aerosol part that's within range, like 80. That's what you expect of smoke. And you have low lidar ratios of the parts of the aerosol layer where there's low depolarization, which indicates maybe that's ice. But what's very interesting is that you have very high lidar ratios in the middle of the aerosol layer. There's like an order of 100, which you don't normally see in the literature. So is it real? It's like, can you have such high variability of lidar ratios inside an aerosol layer? Is it reasonable to have a lidar ratio that's 100 or more for aerosols? It's hard to say. So the unfortunate thing is, and like what any other lidar expert struggles with, is that calibration parameters introduces systematic biases. So one of the calibration parameters that we always struggle with is what we call the overlap function, which is basically the field of view of the instrument, which is unfortunately a function of time, because solar radiation that heats up the instrument, some optical element changes by a micrometer or less, then the viewing angle or the field of view changes, and that has a large influence on your retrieval of the extinction cross-section and the lidar ratio. But since most of the calibration parameters change slowly as a function of time, so even though you do have systematic biases due to the calibration parameters, which change slowly as a function of time, we think these lidar ratios are legit, or this variation of the lidar ratio is legit inside the cloud. It's just hard to say what the actual values are, but we can say, I think you can argue that lidar ratios changes significantly in the aerosol layer. So I just show you, that's a very interesting result that we recently acquired. So the potential benefits of the algorithms we are developing is that obviously we can do retrievals of the extinction cross-section and the backscatter cross-section for lower SNR data, meaning that we can work with higher resolution imagery, therefore reducing systematic biases of the extinction cross-section and the backscatter cross-section. That's one benefit. And since we were working with lower SNR data, another benefit is, can you change the optical properties or the optical equipment of a LiDAR instrument? For example, reducing the laser energy you need to transmit, meaning that you reduce the cost of your LiDAR instrument. There's maybe one benefit of using those algorithms. It's like doing a cost-risk benefit trade-off between using algorithms versus putting more effort into building the instrument. The implications of it will be that you have cheaper LiDAR instruments that more people can buy, like those that Matt is producing and Scott, or you have an instrument that's in space that's cheaper to build, it's more affordable, hopefully Congress will pass it, more people will be happy, scientists will be happy. So that's the potential benefits. But before we can get there to do more hardcore denoising and to make a bigger impact on LiDAR imagery, space-based LiDAR imagery, there's further things we have to do. I have a long to-do list. With the Calliope instrument that's on board the Calypso satellite, it doesn't do phone counting, and it uses PMTs to measure the incoming photons, and they measure the analog output of the PMT, meaning that the noise that you deal with is entirely different compared to phone counting systems. You have a different type of noise source. To model that is much harder, given the type of noise it is. So that's something we have to consider in our future research, is to see if our models are still applicable on analog mode LiDAR systems, and if it's not, what changes do we have to make, or how should the models be readapted? And the question is, okay, LiDAR instruments like CATS that's on board the International Space Station and Calliope, they have much lower SNR data compared to ground-based LiDAR instruments. So our algorithms can make a potential benefit, or we can make improvements on the measurements they are making, but what else can we do to further improve the measurements they're making? It's like, can we work with very low SNR data, like single-digit photon counts? It's like, is that even a possibility to retrieve anything out of single-digit photon counts? So that's future research. Like I said in the beginning of the slide, I just want to remind you, we haven't achieved our goal yet of denoising space-based LiDAR instruments, but we're getting there eventually. But we've made strides, we're using ground-based LiDAR instruments. So in summary, in conclusion, I explained to you the current way that retrievals of the extinction cross-section is done using low pulse filters, using et al. Method, and what other people are using. And I showed you the inadequate results it give. And then the problems that it introduce, for example, biases and artifacts that introduce an extinction cross-section and LiDAR ratio retrievals. I explained to you how the new approach works to retrieve the extinction cross-section. I explained to you how it works. And I showed you it's much better than the current way that the extinction cross-section is estimated. There are many research opportunities, not only for me, but for many other people, to take existing algorithms that has been developed in medical imaging and other fields and see if it works in remote sensing and LiDAR, maybe even radar. And further improvements can be made in remote sensing by leveraging advances that have been made in signal processing. And so I would say the future for making improvements in remote sensing is bright. And that concludes my talk. Thank you for listening. Are there any questions?
Nice talk.
Thank you.
So I guess the question is you apply all your denoising to the rawest photon counts.
Yes.
Can you explain or talk to why you would do it to the raw signals instead of, so you denoise the raw signals, turn the crank, get to extinction. Why you would do it to the raw signals as opposed to anywhere along?
The primary reason is that we want to, okay, let me try it again. If you take photon counting noise and you do any algebraic manipulation on it, you change its statistical properties. It's no longer described by the Poisson probability mass function. That's the major drawback. So that is why we use the most raw as possible data so that we can use the noise model.
So one thing that occurs to me is there's a number of things we use that at least we assume have Poisson statistics. An application for this might actually be particle probes.
Okay. What is particle probes?
So in those cases, we're basically sizing particles one at a time, and we accumulate them over a certain distance. So is it possible that we could use this to get higher time resolution particle size distributions, perhaps, in high density clouds than it would kind of use a longer averaging span in the lower density regions?
So just to understand the problem, what do you count? I just want to understand the problem.
So what happens is the particle flies through a laser beam,
Mm-hmm.
and based on the scattered energy, we infer a size from that.
Oh, okay.
So then we put that into a size bin.
Oh, okay.
And we do that over and over and over and accumulate a histogram. What's our minimum size or time resolution for that?
10 hertz.
So I get 10 hertz. Obviously, we'd like to get...
This is aircraft.
Okay.
Yeah.
So flying through a cloud and kind of
Okay.
sizing it.
So your products are a histogram, and you try to get an accurate histogram, and you acquire a lot of data to get an accurate histogram.
We'd like this to be as high of resolution, spatial resolution as possible, but then you're also fighting statistics, right?
Sure. If the Poisson model is a good model that describes your problem, sure, yeah. And we could probably derive uncertainties for it and see what the uncertainties should be. Yeah, I think if I fully understand the problem, I could say more, but from what I hear now, yeah.
It sounds like it'd be pretty applicable.
Mm-hmm.
Yeah, you mentioned about the a priori of LiDAR ratio to get your thing. To know the a priori, you need to have some kind of covariance functions and few things like that. That's what you talked about, the 2D variations.
Yeah, so I guess we don't use explicitly covariances.
Mm-hmm.
I guess, so where I would imagine where you need a covariance, if you have a Bayesian model, it's like you use, let's say, optimal estimation to do your retrievals. So that's one philosophy or one way of doing things. But rather than describing your signal in a probabilistic way, we say rather, we don't know what its probabilistic model is, but we say it has a smoothness property. It can be described accurately by a mathematical function. And the mathematical function is being piecewise constant in a two-dimensional space. So you don't need explicit covariances. It's more that you estimate a type of function, and that type of function sort of encodes that covariances.
Yeah, in that case, okay. Then how do you get the a priori LiDAR ratios in your thing? What kind of assumptions you got?
The assumption that I make of the LiDAR ratio is very specific. It is greater or equal to 1, like it's lower bounded. It doesn't necessarily have an upper bound, but you can define an upper bound for it. And it's piecewise constant, two-dimensional piecewise constant. That's the only assumptions that we make.
Thank you. I have one other question. How does it relate to wavelets? Could use wavelets for stochastically varying noise like that, denoising using wavelets. How is that your thing related to wavelets analysis somehow, or it's kind of?
It's similar to wavelet analysis. So if we become more technical and introduce some mathematical concepts. So basically, with wavelets, you have a model that describes the smoothness properties of your signal. And we know that if you were to apply this model onto your signal, you only need a few amount of coefficients that can be applied in the model to reconstruct the signal. And that's what I call sparsity. It's like you have the model that describes your function that is piecewise smooth, and you know a priori that you only need a very few coefficients that can be applied in the model to reconstruct your piecewise smooth signal. So then you can describe it in a mathematical way. It's like, here's my model of my signal, let's estimate the coefficients that was applied on the model to get our signal, but our constraint is that only very few coefficients can be applied on the model. What they call it, they say you make sure that your coefficients, or the coefficients you're trying to estimate, are sparse, and that can be described in a mathematical way. What we are doing is that we don't necessarily use wavelets, but we use discrete derivatives. You say that your extinction cross-section, or no, let me backtrack, that the Lidar ratio, if you were to take the discrete derivative over the altitude axis and over the temporal axis, the discrete derivative should have more zeros than non-zero values, meaning that it has to be sparse in a discrete derivative space. And a signal that's sparse and the discrete derivative space is piecewise constant, two-dimensional. So that's a concept that's used in wavelet analysis that's applied in total variation denoising. I hope that answered your question.
I think that's good. Yeah, thanks. Good results. Thank you.
All right.
I'm not sure I understand the scale on which your method operates. I'm thinking of the molecular channel profile you showed, the noisy profile, and then the piecewise fit. What determines the scale on which you...
So what do you mean the scale, like the resolution of the image? Or?
Well, let's say the altitude scale,
Okay.
over which you draw a straight line.
Okay, so the raw resolution is for the altitude axis, 7.5 meters. I have to get some result, I have to reduce the resolution and try to reduce it to a minimum resolution. So the results I showed you, the range resolution or the altitude resolution was 15 meters. So if the smallest line that you can fit is 15 meters, but it's usually more than 15 meters. And then the temporal resolution is 60 seconds with a minute. So the smallest lines you can fit is, or the smallest piecewise constant block that you can fit is 15 meters by 60 seconds. With the Lidar ratio, because it doesn't change much, because you leverage the backscatter cross-section, it doesn't vary at that high frequency. It varies maybe by 100 meters or less, between 50 and 100, if I had to guess, if I just to pull numbers out of my head.
Yeah, sorry, just to follow up on that. There were portions of that curve where the profile of the molecular channel, the red and blue.
Oh, okay. Oh, okay.
The red line is not what I would draw by eye.
Well, yes. What will you draw? I wouldn't draw it. I will draw something else, but I would like to know what you would draw.
Well, okay. Let's pick a spot at just below 13.5 kilometers.
Yeah. You mean over here?
On the right side, yeah.
What will you draw?
Well, between 13 and 13.5.
Yeah.
In the middle there. There's a low spot in photon counts. Exactly.
Oh, okay. Wait, over here.
So I'm wondering what. Yeah. So how's the method bypassing that and saying I want to draw a straight line, but not through those data points?
It's a good question. So what I didn't explain to you, that was just lengthened to talk, is that we basically have two sets of observations that are independent from each other. Just to go quickly over it, we could take existing photon counts and we can split the photon counts, that we have two independent copies of the photon counts using a technique we call Poisson thinning. And because they're statistically independent from each other, it means that if we do an estimate over the one copy of the photon counts, we can verify if it fits the other copy. In other words, if you were to have a second copy of the photon counts of the molecular channel, it will be, since it's a noisy signal, that you won't necessarily see like maybe 3 consecutive photon counts that is smaller than the average. The other copy of the photon count, it won't be exactly the same, it will vary. So the basic gist is that because you have two statistically independent copies of the molecular channel photon counts, You can do the estimation on the one, and you verify if it fits the other one. So you bypass the issue that you do a fit on where it seems that it should be smaller. If you were to do a fit over here, where it's smaller, and you were to verify your estimate on the second copy, it will be off, because you won't see those 4 or 3 consecutive phone counts. So yeah, basically, said another way, what they call it in statistics, they call it cross-validation. We do cross-validation of our estimates.
So to clarify, the blue is actually the validation set.
I think it was the actual phone counts that we used to do the estimation. I can't remember, to be exact.
So is the reason that this is too difficult so far to do from satellite, that the satellite is moving so fast and horizontal inhomogeneity is so large that it doesn't make sense to, it's too hard to find horizontally homogeneous samples to get enough samples to say this is actually a uniform region?
The reason why we haven't been working on satellite-based data is that I was not able to get data, or raw data, because we need raw data of the satellite imagery. It's like, I don't know what your name, Harvard. Robert asked me, it's like, why do you use the raw phone counts? Like, why don't you use process data? It's like, we need the raw data so that we can use the statistical model that describes the raw data. And yeah, it's only recently that we were able to get raw data from the CATS LiDAR instrument that I'm started to work with. So I'm busy working on CATS data, but not on Calliope data.
But the question remains, does horizontal inhomogeneity tend to stuff up what you do from a satellite because it's moving so fast that you have relatively raw, low resolution?
Oh, that's a good question. Sorry, I missed that question. Okay, so it's too bad we don't have a meter scale for the horizontal axis, because I would be able to tell you. But yeah, if you have a lower resolution image, you don't have much homogeneity, so that will work against you. So for water clouds, which is highly variable, you will have problems. But with aerosol layers, I can't tell you how many profiles you would need, but it will definitely be the case because they're slowly varying and they're expanded over more profiles, maybe 30 profiles. You will be able to use the algorithm for that.
If I understand correctly, you have to develop a noise model for going to analog.
Yes.
But so you could apply this for CATS now, using the same model you have.
Yes. Well, except that CATS is a standard backscatter LiDAR. And another issue is they have much lower SNR. So the current techniques will work, but we can do better. There's better algorithms that exist that will be able to produce better results for very low SNR CATS data.
And then so moving to something like radar, you would have to come up with a model of the noise of the radar detector as well, right?
Yes.
And that's the key.
Yeah, because you need a noise model that describes to you how your estimates fits the noisy observations.
All right. I think with that, let's thank Willem one more time.